Now we come to the topic of isomers or isomerism. So this is a last topic of coordination chemistry, but if you talk about isomers, that's mainly a topic of organic chemistry. That is where we actually learn isomers, that is your position isomerism, chain isomerism and whatnot. But coordination compounds, even though they are inorganic, but they still show isomerism. So in the next slides, we are going to see the type of isomerism which are exhibited by coordination complexes. So what are isomers? Now this definition we have been studying from class 10th. So it has been marked up and put it into our brains through osmosis right now. So isomers of a compound have the same chemical formula, but the arrangement of atoms are different. Okay, that is the basic definition that is applicable for your organic as well as your inorganic chemistry. Now isomers are of two types. We have structural isomers and stereoisomers. Till now we have the same thing going on in as in organic chemistry. In organic chemistry also we have structural isomers and we have stereoisomers. Now further classification is where the difference arises. In coordination compounds, the structural isomers can be classified as ionization isomers, hydrate isomers. Hydrate isomers are also known as solvate isomers, coordination isomers, linkage isomers and coordination position isomers. So what are all of these and what are structural isomers and how they are different from stereoisomers, we are going to learn in our coming slides. Whereas stereoisomers are classified as geometrical isomers and optical isomers. So now let's see what is the difference between structural isomers and stereoisomers. The difference between structural isomers and stereoisomers is that in structural isomers the connectivity changes. The connectivity between the carbon-carbon changes. Whereas in stereoisomers the connectivity does not change, only the orientation changes. If I take an example of organic chemistry, you'll be able to understand that better. So let's just take an example of organic chemistry right now. These are structural isomers. You can see the connectivity between the carbon atoms is changing. If I name this carbon atom as 1, okay, and this is 2, this is 3, this is 4 and that's carbon atom 5, and then if this is 1, 2, 3, 4 and 5. So you will be able to see that the molecular formula remains the same, but in this one, the fourth carbon is attached to the third carbon, whereas in this the entire structure is different. The fourth carbon is attached to the second carbon. Connectivity is changing. Whereas stereoisomers, when I talk about stereoisomers, you can see the connectivity is not changing. This carbon was attached to CH3 and Cl and another carbon. This carbon is still attached to CH3, Cl and another carbon. This carbon was attached to CH3, Cl and another carbon, and this carbon is still attached to CH3, Cl and another carbon. Connectivity has remained the same. What has changed? The orientation of the molecules in space has changed. This CH3 was surrounded by one chlorine from this side, one chlorine from this side. Now this CH3 is surrounded by one chlorine from here and one CH3. So its surrounding has changed and its orientation has changed. So that is what is changing. That is what is the difference between structural isomers and stereoisomers. Another example we can take of stereoisomers, like if I have carbon, to carbon there is an SH attached, there is an OH attached, there is a Cl attached and there is a bromine attached. Its optical isomer, let me just clear the board a little. To this carbon SH is attached, Br is attached, Cl is attached, and OH is attached. Now these both exhibit stereoisomerism. You can see that the connectivity is the same. Carbon is still connected to SH, OH, Br and chlorine in both of these. What is changing is the orientation of the OH and the Cl. That is what is changing. Okay. So these both are stereoisomers. These both are also stereoisomers. The first two examples I gave you are structural isomers.